We're about 50 people right now. It varies this year because of the situation that we're in. We are on a fairly rapid growth trajectory starting for 2021, so we're extremely pleased with that. And we have some machine time, so we're looking for some more business.
Now, didn't you guys recently expand and build a new, facility?
That is correct. We just recently built out another 6,700 square feet of clean room space. Right now it's rated at class 100,000. We have the capability of rating that down to class 10,000 if necessary. Right now the processing that's being done in that building, it's not necessary for it to be quite that robust as far as the clean room design is concerned. But if the right project comes along, we'll recertify the clean room and move forward with the project.
All right, awesome. And Julian, tell us a little bit about your background as the thermoplastic extrusion manager.
All right, hello everybody. My name is Julian Stralahorn. I am the melt thermoplastic manager, and I'm originally a California transplant. Been out in Arizona for 8 years and have been extruding here in Arizona for 7 years. So we have multiple different projects that I've taken the lead on, and I enjoy the challenging aspect of some of the projects we've worked on.
And how did you get into thermoplastic extrusions?
I think we offered him a job.
Yeah.
and then we trained him.
yeah. I had a Toyota production experience with a lot of the Kaizen, and a lot of the experience I took from that job, some of it was able to translate into a production here. Mm-hmm. But that was my root was in production for Toyota. But then Tony offered me a job, and I took it, and I've been rocking ever since. Been knocking it out the park.
All right, awesome. So basically, let's talk a little bit about because I know that people want to know how they can reduce the costs of their thermoplastic extrusions, and we're going to get into a lot of that kind of stuff here. And so what we know that IPE has been pretty much best known for EPTFE extrusions and a lot of clean room extrusions and that kind of thing. Everything from extruding EPTFE and PTFE sutures all the way up through tubes, rods, and sheets. So how did you guys get involved with thermoplastic extrusions, and how long have you been doing it?
I'll take that one. So we purchased our first melt thermoplastic extruder. It was 1992 or 1993. I don't recall the exact date. And basically what we were doing at that point in time was single lumen, small diameter tubing for the telecommunications industry. As the company grew, we began to see a need for marrying the melt thermoplastic materials together with the porous PTFE that we produce here. And so what we've got is a situation where we can take the porous PTFE, we can reflow let's say a nylon or an FEP tube onto the end of this porous PTFE, and we've gotten fairly large projects associated with that, mainly for catheter applications and robotic surgical applications. Now, as far as most of the melt thermoplastic projects that we've worked on, a lot of them have been not simply just a plain tube. In the early 2000s, we worked on an inhalation device, which was basically a pump, had a polyurethane tube with basically 3 or 4 features on it. Both ends were expanded to accept a lure connector. And then in the middle was a curlicue that had to be in the perfect spot so it didn't interfere with the pumping mechanism on the delivery device. Those are just some of the larger projects that we've worked on in recent years.
All right, and so in terms of cost reductions and that kind of thing, I mean, what are the key elements? What are like the 3 to 5 key elements that go into thermoplastic extrusions and that determine the cost of what the final extrusion is going to end up being?
Well, one of the key issues is being able to prototype with a less expensive material. And we've seen some success with that, where we'll test our die design, we'll test our flow rates with a material that might be similar, but it might not have all of the compounds in it. So if we're looking for fire retardancy, or if we're looking for maybe being able to see it under X-ray, we might extrude with the base material in order to get the tooling geometry correct if for some reason it's a profile or something along those lines. Normally a tube, unless it's a very thin wall and a very large diameter, is a slam dunk for us. Larger tubing like that can be a challenge. We've mastered that up to about 675 thousandths. And so, and that's, I believe that was a PBAX project.
Yeah.
So Julian was challenged with that particular project and came out like a rock star. So that thing worked really well.
Well, I mean, on that subject, I mean, Julian, tell me a little bit about that project. What some of the challenges you ran into and overcame to, make sure that the customer was well taken care of?
Well, it was pretty thin, but and we're running this hot molten material through a vacuum, and we're trying to blow it up at the same time. So we have to be mindful of the surface area, because we want it to be flawless. We want to try our best to make it look presentable. So you have to worry about getting the perfect OD. The wall has to be perfect, and has to be visually
acceptable.
Yeah. So it does take a little time. I mean, especially if it's the first time we're doing it, but we will not give up.
Let's address the cost reduction side of that. Basically, what we're doing is we're looking at putting together a project that has a specific plan, and instead of just throwing some tooling together and making the machine do what we want it to do, we'll do the calculations. If for some reason we've got extra features to add, we'll get our engineering group involved, and we're always looking at some way to control cost. If we can control cost on our end, we can pass that savings on to our customers, and that's always been our goal and our one of our main aspects of manufacturing here. A lot of the materials that we extrude around here we've done so many projects. We've got probably a piece of this and a piece, or 10 pounds of this, 15 pounds of that laying around. And so we can prototype rather rapidly. A lot of times when somebody's developing a catheter, they might just need something quick, meaning don't care what kind of material it is. I just need to do proof of concept on pushability or placeability or something along those lines. And so with our inventory, we'll usually be able to knock something out fairly quickly. Now it won't be a whole lot of parts, but we can get you something in a fairly rapid manner.
Got it. And so now in terms of I mean, basically from what what part does the type of equipment play overall in the overall scheme of cost for your thermoplastic extrusions?
I'm going to take part of that. And then I'm going to let you finish. So in 2015, we purchased a state-of-the-art machine from American Coon. It came with 3 barrels. We've got a 1 inch, 1.25 inches, and 1.5 inches. So we've got quite a bit of capacity there. It also came with updated software from our 1992 machine that we had simply worn out. And I want to let Julian address some of the challenges that we had with the older machine and some of the features that we have with the new machine that helps us achieve that cost reduction goal that's key to everybody ordering our products.
Yeah, so with the old machine, it was old, you know, I mean, things start to break down eventually. And it may take longer time to do R&D on a part when you have fluctuation in the size of the part. With this new machine, it's it's a lot more easier to make these parts. It's more reliable, and our Zoom box is great. When it tells us, we get so many different readings.
Talk about the idea.
Yeah, I mean, we can set it up to as we're about to start collecting or in the middle of a project, if the size does fluctuate, it will kick off bad parts continuously and alarm us.
We can make adjustments in order to bring the process back under control.
And it can do it automatically too. And so we can set it up so that way the machine will make adjustments automatically. If it does go out of spec, it will adjust. So it's once everything's dialed in and set up in the manufacturing part, we could just make parts all day long. And any issues that arise, either the machine will do it automatically, or the person in there that's watching the part can make adjustments too.
So so it's also, and then I'm assuming also it'll keep your tolerances a lot tighter and allow you to make more complex parts.
Yes,
that is correct.
Got it. Now, what about now we're talking about what are some of the limitations that you guys have in terms of die size and that kind of thing, and in terms of, I mean, when you're talking about in general extrusions, because I know that some places, some places you're talking about gigantic extrusions. You're talking, 10, 12-inch, whatever size extrusions, and you guys specialize in much smaller diameter extrusions, right?
Much smaller, very precise extrusions. Currently, we're only a single layer design with the exception of overcoating materials. We do have a setup for doing that. So we can lay down 2 layers. It's just not ideal at this point. We do have some projects in the works right now where we would be looking at a micro extruder in order to introduce a very thin layer over the outside of another material. So we would have a 2-layer design at that point. That project probably won't mature for about 8 months. And so we won't have that capability for, some time in the future. But those are some of the growth opportunities that we're looking at. Now, as far as the tooling is concerned, we have our own machine shop here, so that if it's a fairly simple material or a simple setup, we can go back, and if we need to bore a few thousandths out of the die or build a new mandrel rather quickly, we can have that done in usually a day, a couple of days max, if we don't have the material in place. So that helps us translate into quicker turnaround, which should reduce cost on the other end of the
Got it. So, I mean, basically in some of our discussions, we decided, we kind of came down to 3 key elements that are, that really determine the largest factors in terms of cost reduction. And those elements are part design or data collection, getting information from the customer about the specific project that they're looking for. And then, of course, there's also the material choice and specifications for that. And then the third element is also the tooling. So I wanted to kind of delve into the first part, which is, part design and data collection from the customer. And we know that, communication is one of the key factors here in the process when you're trying to develop a new part for a customer. And, before we go into the part design, what are some of the key things that you need to find out from the customer in the early phases of the project so that you can work with them to help guide them?
So yeah, if there is the tolerance, how tight the tolerances need to be, or would they be willing to, if there's any issues in the future, if we go in production, would they be willing to open up the tolerances? That would definitely let us know what we can do.
It'll help us to reduce the any type of waste that we have. Again, that reduces the cost of the overall project.
So that's what, when it comes to the part aspect of it, yes, the tolerances, and then we have the material too. If there's a history, if they have feedback from, if there's a history with the material that they're recommending, then that would definitely help us out. You know, if we know any information we can get on the material would definitely help us out for how we're going to set up the job.
Got it.
To kind of readdress that a little bit, the we have a lot of specialty materials around there, like Peak and Ketaspire, or not Ketaspire, what is the other one?
Right. Yeah.
Ketaspire. And anyway, those are highly specialized materials, and they're quite expensive. And so when we get back to this tool design, this die design, we'll do dry runs with a lot less expensive material.
Mm-hmm.
And again, that helps us to do our proof of concept, and then allows us to move forward.
Got it. Now, what about environmental factors and of course part geometry and that kind of thing? I mean, how does that play, and strength requirements? I mean, how does all that stuff play into the cost?
Well, part geometry can be a challenge especially if it's a
Crazy profile.
Yeah, thin wall, or like Julian said, crazy profile.
We've had some challenging profiles, and but we've been able to knock it out the park and make some good looking profiles. Even though it seems complicated at first, but we have a good team,
Mm-hmm.
and we can take care of some complex profiles as long as it's.
We've got one that's a rather interesting profile. It looks like there's a little part that goes into it that looks like a tiny surfboard.
Mm-hmm.
And that part is an introducer for a facelift device. And it's bioabsorbable. So the material is cut at an angle and it's burnished on the end. And it looks like an upside down W when you look at it. And it's simply for placing the medical product or the bioabsorbable somewhere in the facial area, and then pulled up for the facelift, and then it slowly absorbs into the body.
Got it. Now,
that one was rather complicated.
So when we're talking about the actual design of the parts, and you're talking to an engineer about their design, I mean, obviously you're looking at the complexity of it, and are there typical, I don't know, for lack of a better term, common mistakes or issues that you kind of see over and over again that engineers and designers are putting into their parts, where you could help them to, if they looked at it a different way, or if they, did something different, that you could help them to reduce the cost of their part?
It kind of goes back to tolerances. One of the biggest challenges that we have is that we might be building a catheter that then goes into some type of introduction device. And there's only a certain amount of real estate there. So the buildup of tolerance for all of the parts that might go into that tube dictates the size of the part that might be necessary from our facility. And so having to address that, find out what kind of real estate's available, and negotiate with the engineering group to see if we can't either minimize our effect on that particular aspect of the device, or tighten our tolerances up if we need to pull things within thousandths or even a half a thousandths with some projects. We can do so. A lot of these newer catheters have a lot of moving parts. Some of them have electrodes that go down through them. Some of them, so let's take something like an example of an endoscope. Right. There's probably 30 parts that go down to the tip of that thing in order to steer it, show light, wash off the camera, biopsy channels, things of that nature. So, our job is to work within the constraints of the engineering group's goals and objectives. And then at some point, if we can get if we can get a little extra tolerance in there, we're always looking for that.
So basically, now do you find that sometimes things are, some of the tolerances are just overkill for the application?
We've seen that in some of the projects where, there might be a part that is maybe of a softer material, say like a thermoset or a thermoplastic elastomer, something along those lines. And you might see an incredible tolerance of plus or minus a half thousandths on something like that. When you actually measure that part, your measurement technique will actually take up most of your tolerance. And so when we do gauge R&R on some of the projects, we'll have to point that out to the engineering team, stating that, hey, you know what, we can meet the tolerances, but our measurement technique is taking up the entire tolerance. So we want to make sure that everybody's aware of that, going in, because there's always a transfer between the engineering team and then the production side.
Right.
The research and development engineering team, they get all the details worked out. We get the parts built the way that they wish to have them built with the correct tolerancing and, the correct configuration. And then it goes to purchasing and production. And what that means is that there's an extra quality step that gets in the middle of that, then during the verification process on the customer side, they might be looking at different aspects of the part, different from what an engineer might look at it.
Got it.
And so we'll have to sit down and talk about how we would measure those parts, how we get to the C = 0, part distribution, so that we have no rejects going out of our facility and into somebody else's facility. And if there is an issue, how to mitigate that issue and change it so that those issues don't occur again. Our quality system's been designed to robustly track that and then provide feedback to the customer in order to address any issues that they might have in their quality systems.
Okay, so now let's move on. Unless are there any other issues in the design or data collection phase that we haven't discussed yet?
Not that I'm aware of. What we're seeing is with the engineering groups that we're dealing with these days, everybody's done one or two. It's when we see the junior engineers that we might need to coach them a little bit. But a lot of the engineering groups that we work with these days are well versed in catheter building and tolerancing and buildup of tolerancing with the different parts that are associated with the project. Got
it. Well, so let's talk. Let's delve into the next part, which is materials here, and how do materials factor in the cost equation? We know that it's not only having to do with the hard cost of the material. There's other things that come into play. And, so what are some of those things in terms of the type of material that you're selecting for the particular product that will also affect the cost?
Well, it doesn't, so for a medical part or a tube. So obviously, if it is medical, then the cost will definitely go up for that material. But for production or for R&D, like Tony said, mentioned earlier, it doesn't have to be. We can find something very similar, like a low density polyethylene that doesn't have to be medical grade to make the tube, just to do the R&D aspect of it, and then we can transition to a medical grade low density polyethylene and then make that tube. The difference is won't be noticeable for a manufacturing part of it, or even the tooling. So if we go in with a project and you want it to be medical grade, we have experience, we have other materials that we can use instead of that out the gate. That'll definitely help the price, at least for that, the beginning aspect of it, with the R&D phase of it.
A couple of other factors too, especially when you get into the high-end engineering resins that have, the steel-like properties. We'll want to make sure that we're in pretty good shape before we start extruding something that costs $100 a pound.
Yeah.
Because waste then becomes a huge factor in the cost of production of the materials. You know, and once we've quoted something, we stick to that. So we will do everything in our power to reduce the costs on our side if for some reason we've misquoted, which doesn't happen often.
Got it.
And with the materials too, we have so much history with different materials, so we can draw on our experience to make sure we have the right tooling, the right heats for the project. You know, so we have history and a large database to go off of to help us work the problem out or this work the project.
I still have the copy of PHR 00001.
Now, do you guys have you guys found typically that materials that are specified in a project are overkill for the application? And if so, how often does that happen? And can you give any examples of how you solved it?
It doesn't happen that often. A lot of times we'll have an engineer access, they'll be broad in the materials that they're interested in. But there are some occasions that that does happen every once in a while that somebody would recommend specific material, and we can recommend something that will work just fine that is cheaper.
And in some cases, easier to get a hold of. We've run into a couple of projects in the past, especially when there was the ethylene crunch of 2017. I mean, that might have been 16, translating into 17. We were having a tough time getting resins. And so at that point, we did make some recommendations to some of our customers to equivalent grades or equivalent formulations from different companies in order to move forward. The only issue with doing something like that is that if it's a medical company, they have to refile with FDA. That can take a while. And usually, well, what happened in 2017 is that we made it by the skin of our teeth, and the resin supplies began to flow again. So those are some of the challenges that we've seen in the past. Again, that probably doesn't translate to cost savings, especially from a customer standpoint. But we're here to make sure that the customer gets the parts that they need. And at some point, in some cases, you're kind of doing everything possible in order to get the parts that you need or that the customer may need, and you may not be focused specifically on cost reduction at that point. But those are project by project issues that come up from time to time, and we don't anticipate that happening in the future. Hopefully not, anyway.
Got it. Now, what about material characteristics and secondary processing? I mean, how does that come into play? And and what about in terms of pliability versus non-pliability and those types of issues?
Well, as far as the materials are concerned, we've seen secondary processing where we've either tried to we've either put a tip on it or put a bulb on it, or we've welded a couple of materials together. That seems to be something that's quite popular these days, is where you've got one material as your base material and then another material that might go over the top of that in order to create an actual stop if it's being passed over an instrument or something along those lines. And also can work for the ID as well, where a material might be being used as a protective sheath and you need a positive stop. So you would marry the two materials together.
Got it. And what about are there any batch to batch consistency issues these days, or material availability and quantities? Are any of those things a factor at all today?
This year, we haven't seen that as being an issue. We've seen it in years past as being an issue. And as far as quantities are concerned, usually when we get a fairly large project, we'll order a gaylord of material. And in the past, that's been sort of a challenge because we've seen from one batch to the next, parameters change in order to get the same run characteristics associated with the tubing or the profile that's being extruded.
Mm-hmm.
With the vendors we're using these days, we don't see that much batch to batch variability. There's still some, but it's not like it was, 15, 20 years ago, where you get one batch in and then the parameters would completely change from the next batch. So I don't know if that's a result of attrition in the marketplace or whether or not the engineering groups have gotten better at building plastics themselves. I suspect it's probably the latter, in that people are understanding the chemistry a little better. They're understanding how to control the process a little better. And we've got these things called computers that can do 1 million calculations a second, so or probably more than that. And those guys are producing some good stuff for us these days.
Got it. Now, do you guys run into many issues about material waste? And I mean, how does that play into obviously the more material you're wasting, the higher the cost goes up.
Yeah.
So
you might see that in the R&D phase, but you won't see that in the production phase.
Yeah, once we go to production, we pretty much have a lockdown. And then, like we mentioned before, if that happens, we can use a cheaper material. Sometimes, sometimes we can get away with using the cheaper material, and that definitely helps cost savings, right? But if we're not able to do that, there might be some at the beginning of the R&D process. But usually, once we have it dialed in, we're good.
Yeah, waste is very minimal.
Toyota, you mean? That's a Toyota. Production, it'd be no waste. We can't waste anything.
So lastly, in terms of this, to wrap this part up, because I know, Tony, we were talking about your spool recycling program, and just wanted to kind of, how does that work, and how does that save the customer money?
So what we've done with some of our customers is we've implemented a system by where we'll ship materials out on spools to them. They'll collect those spools over time, and then they'll ship them back. As long as that's appropriate for their particular process, we have a method by which we can take care of that, get the spools back in here, get them cleaned up, and if they need clean, toss out the ones that might have a chip or something in them, and recycle those back to either that customer or another customer that we've entered into a supply agreement that allows us to do that. Mm-hmm. That kind of brings up an interesting point, is that we do enter into supply agreements with our customers in order to define, what role each one of us has in making sure that the parts that come to not only our facility but to their facility meet the specifications of both of us. Mm-hmm. That way, it's more of a partnership rather than a challenge in order to get parts out to the customer on a regular basis.
Got it. All right, well, let's talk a little bit about tooling then, which is one of the last keys. What factors should customers look at when they're designing tooling and when they're, purchasing tooling for their extrusion?
Well, you need to look at flow characteristics of plastics. If for some reason you might have an oval with a bulb on the end or something like that. We've seen strange designs like that before. With no explanation as to why that bulb needed to be there. That's a huge challenge for us, not only from a tooling design aspect, but from a flow characteristic aspect. We've been able to achieve that by, making dams and things like that in the helicoid and changing the flow characteristics of the plastic. It's not something that we typically want to do, but stranger designs usually create a little bit of an interesting project. And once we get one of those, then we try to negotiate a situation where we can design the tool around an equal flow of product coming out of the die. Mm-hmm. Meaning we don't have high pressure spots or low pressure spots, or even voids where we wouldn't get plastic to flow.
Got it. So then of course, and that also comes back to the first part, which is, communication between you and the customer right at the beginning in terms of data collection and finding out, well, why is the bulb in there? So that way you can help them to address that issue if it needs to be there or not. And
maybe it's an issue with reinforcement.
Right.
And maybe we can put a wire in the wall or something like that. So
there's there's those things that help with the communication. Now, is it better for the customer to get the tooling done independently of your shop, or is it better for them to have you guys just take care of the tooling, or have any shop take care of the tooling? If they're going to, depending on which extruder they end up going to, is it better to just have them do it all, or to have it separate?
It's better if we take care of that aspect of it. And what's happened in the past is we've worked on projects when we've had to open up. We've on some profiles we've had some issues with the part, and we're trying to figure out what's going on. We'll be able to communicate with our engineers in the back, come up with a plan, and we'll make a few changes to the tooling that we have on hand, knock it out to park. So the fact that we have a great set of guys in the back that can help us out with tooling helps us out a lot, time and stress. So those guys are really cool in the back. So definitely we do that in-house. We can communicate with each other and work together as a team to knock it out. So that's what it's best that we take on the responsibility of the tooling here.
Got it. And I mean, in terms of the tooling, and what about how many iterations does it usually take to get the dies and the parts done right for a project? What should customers expect in that regard?
Well, with a complicated profile, it can take up to 3 times in order to get the geometry correct. And like I mentioned before, you might have a void where you're not getting the correct plastic flow or material flow into an area. And so you might have to do some modifications on the back end to get better flow in that area. Mm-hmm. You can change the design of the blunt mandrel. You can change the die characteristics itself, and provide a better flow rate in those areas where you're having a tough time getting the correct wall or something along those lines. We make some really neat bumpers for circuit boards, so that when they're going through their process, when they bounce off of each other, they're bouncing off of our little bumper, and that seems to that one was quite the challenge to build.
Mm-hmm. It was fun. At first, it was a little frustrating, but you know what? I mean, working together with the guys in the back, it was pretty cool the way we knocked it out, and it was really interesting. I enjoyed that.
That one was a neat project, and now it just runs. You just set it up and it runs.
Yeah. So as long as it's not overly for tooling, as long as it's not overly complex, mm-hmm. If we can, it can be done.
Yeah, I mean, picture what was that? Picture a square top with some legs on the bottom. That's basically what it looks like.
Now, what about lead times on getting tooling made and the run life of a set of tooling?
Well, as far as getting tooling made, as long as it's a round profile or even something that we could mill here, we can build that here in-house. Anything that has to be EDM'd, we have to send that out. So we're at the mercy of our vendors at that point. Right now, things are running around 4 weeks for delivery. We've seen them as quick as a week and a half. It all depends on what type of materials are being run at some of the machine shops that we use for EDM work. Mm-hmm. Right now, the lead times are bumping back up. So we're usually under the gun in order to get parts out the door once we get the tooling back, as the lead times increase from our vendors.
For a tube, we can go pretty quick. We've gotten
We did that today.
Yeah, knocked it out really quick. But the profiles EDM stuff takes a while.
Yeah.
Now, tell me what this, what the 2 is 1 and 1 is none concept is.
That's
But-
So during production, you can run into problems, and if you have an issue with a set of tooling, it's always nice to be able to fall back on another set. Especially if you're right in the middle of a project that's hot. So I always think it's best to have another set of tooling to fall back on that, so we can just get it up and going and keep the ball rolling.
Mhm.
You don't want to be stuck waiting for a new part to be designed, especially if the guys if they're backed up in the back in the house.
Right.
Wait a little bit, or even for getting something EDM, that could be a while. So I always recommend we having 2 sets of tooling.
So that basically is that's a real good, I mean, especially for longer production runs and that kind of thing, that's a really good stopgap measure to make, kind of like, it's like buying insurance essentially.
Exactly.
And so now, we're coming to the end of our time here. But I wanted to kind of get into, some of the other factors that may, come into consideration to reduce costs of the, of the extrusions. I mean, what about, when we're talking about part volumes and, talking about, material quantities and, Kanban, part availability, lead times. I mean, just in general, what are some of those things that all, just kind of play into that?
You mentioned a whole series of cost reduction measures that can be achieved, again, through supply agreements and things of that nature. We do enter into Kanban agreements where we'll keep a certain amount of parts here on our shelves, so that if the volumes ebb and flow, so to speak, we have some safety stock available. We also have some stock available if for some reason somebody runs into a situation where they receive a rather large order and we need to get something out the door right away.
Got it.
As far as material volumes are concerned, we like to right size that, maybe keep 3 to 6 months supply on hand, depending on what type of material it is. That way we can set up a system where we've got plenty of material available. We get the volume discount on the pricing, and things of that nature. So, got
it. Okay. So I got a couple of other questions here from some of our participants.
Okay.
One is question one is, by referring to plastic flow characteristics, do you mean the manufacturer mainly in the fluoropolymers, or mainly of the fluoropolymers in terms of the plastic flow characteristics?
We've done some work with that in the past, but no, mainly the product, the plastic flow characteristics of melt thermoplastics, things that you can heat up in temperature, and basically change their shape by just increasing the heat. PTFE, or at least the PTFE that we extrude here is a paste extrusion. We have done some ETFEs and some PFAs. Those are the melt side of the PTFE type materials, and we've got experience with those, and some of them are quite expensive. Well, we ran one the other day that was $103 a pound or something like that. We didn't waste any of that.
And what's your experience with higher reduction ratios or lower? I'm assuming the question was, your experience for in higher reduction ratios, or is it lower for fluoropolymers?
Well, it kind of depends on the tubing that you're trying to extrude. If we're talking a paste extrusion, the paste extrusion is We've got a certain reduction ratio that range that we work within. We've pushed that envelope with different materials. And so anything is possible with enough engineering time and patience. What we've seen is that with the melt thermoplastic extrusion side, that's one of the reasons that we have 3 barrels in one machine. If we need something to, if we need to build something that you know, that has a high reduction ratio from like a FEP or a PFA standpoint, we'll use a larger barrel because that'll require a larger drawdown.
Got it. Okay. And so, you know, real, you know, quickly in review, I mean, basically we've got, you know, when we're talking about cost reduction or, you know, being able to identify any of those factors, obviously the number one thing is, as early in the process of your project, you want to get in touch with your vendor to coordinate with them to start the discussions about, you know, about the project and what can and can't be done, and to get as much input from you as possible. And that was, you know, one of the takeaways. Another takeaway that I also, you know, gather obviously is, you know, I mean, it seems as though most of the cost reductions occur in the R&D phase, correct?
That is correct, yes. One of the biggest challenges that we run into when we're trying to quote a project is that we'll get some outrageous number where we're going to build 4 million units, and which is not a problem, with the exception of if it doesn't mature correctly. Mm-hmm. So what we'll try to do is we'll try to right size the project so that we get, and I kind of alluded to this in the materials section, but try to right size the project so that we get the best discount that we can get from a resin supply standpoint so that we can pass those savings on to our customers.
Got it. And, you know, so obviously that's all a key. And now, if, you know, what factors should your customer or, you know, engineers and whatnot, what are the things that they should really watch for when they're trying to find a thermoplastic extruder?
Well, on-time delivery is a big one. The ability to sort of react on the fly is another. We have multiple projects coming through the facility these days that require that changes be made almost instantaneously. Mm-hmm. And in some cases, we're relying on vendors that don't allow us to do that. That's why we've tried to integrate both the porous PTFE manufacturing, and the melt thermoplastic manufacturing, all integrated into one facility. One facility. One of the, and I kind of lost track of the question there, but my point being is that we're kind of a one-stop shop for building machinery and equipment, as well as materials. What I mean by machinery and equipment, for some reason it needs a bulb on the end or it needs to be tipped in some fashion, we can actually build a machine here that will do that in our machine shop.
Got it. So basically then, if you're looking for a company to run thermoplastic extrusions for you, then then certainly in-house capabilities is definitely a factor, correct?
Yes, that is correct.
And in terms of and problem solving and upfront communication as well, right?
That is correct. The best way to do projects is, especially if it's a rather large one, is get everybody in a room together, at least in the beginning, mm-hmm. and then fan out to the different engineering disciplines in order to get the correct materials.
Got it. Here's another question that popped up. Would you agree that higher shrink ratios of heat shrink tubes in FEP tube using a higher I think that's MFL.
Melt flow rate, yep.
Yeah.
Okay.
So,
well, unfortunately, I'm not well versed in heat shrink tubing because we don't make any of that here.
okay, got it.
We use it, and we've seen we can kind of go into some of the challenges that we've seen with heat shrink tubing. One of the biggest challenges that we see is the fact that if the wall is not perfectly concentric, we can see different shrink ratios on different sides of the tubes, which in some cases throw one side of the tube out of tolerance and the other side will be in tolerance if we're, for instance, reflowing it onto another part.
Oh, okay.
So that's one of the biggest challenges that we've seen. I would like to be able to build my own heat shrink tubing. We're not quite there yet.
Got it. All right. Okay, well, I think that, basically, we've gone over pretty much everything, the key elements being data collection, main area up front, communication with the engineer, really getting all the specs under control, finding out what they are, how it relates to the materials that are going to be used in the end product. If there's going to be enough material available and what the specifications of that material are, and if you can, possibly find something else that's going to work just as well for whatever the specs are to the with the customer. And then, of course, always making sure that whoever's doing your thermoplastic extrusions is actually the one that's also taking care of the tooling as well. And in the case of larger production runs, having multiple sets of tooling to be able to work with that.
Yes.
And let's see. Okay, here's a comment. Our experience is that we use 3 melt flow indexes for lower shrink ratios and 36 melt flow index for 2-to-1 shrink ratio. And he wants to know what your comments are on that.
Well, there's a limit to what we can handle for a melt flow rate. Usually anything above 22 is proven to be extremely difficult for us to extrude on our end. It's just, we can throw like 7, 8, 10 screen packs at something that that has a 20 or 22 melt flow rate. When you get up to 30 or 36, there's nothing really we can make with that. Maybe we can coat something with that on our end, but when it comes to making a tube or anything that has a high melt flow rate, it won't. It's just liquid. It's just we can't produce anything. We haven't produced anything with that high melt flow rate.
Got it. So now are there extruders that will produce the things with that kind of a melt flow rate, or is that kind of outside of the general scope of most extruders?
To be honest with you, I don't know how to answer that.
For our end, we've had difficulty extruding material that has a very high melt flow rate.
Yep. I know with Delrin. Delrin was an extremely challenging material to extrude. We were able to extrude it finally, but it was extremely challenging to get to where we needed to be with that particular project.
Got it. All right. Yeah, and the questioner said basically they use it for cable and tube for IV cannula in India. So that's how they're using it.
Okay, yeah, it would be some type of a coating material more than likely. I don't think it's a free extrusion.
All right, so I think that pretty much we're wrapped up here at this point. Are there any other closing comments that you guys would like to make before we end our webinar?
I saw that there was another question come in, but I just wanted to thank everybody for their time. I know that these things can get a little boring. Hopefully we were somewhat entertaining.
First one, be easy on us. Be easy on us.
Yeah, entertaining and informative. That's the important thing.
That's the whole idea behind this series. So.
All right. Well, thank you guys very much, and until next time, we'll have plenty more to come up next year.
Wonderful. Can't wait for the next subject. Take care.
Got it. All right.
Thank you, everybody.
All right, guys.
Bye.
Bye-bye.